Hi, my name is Arlen, and my submission for the Service Science Best Student Paper Competition is titled Learning Bundle Pricing of Reusable Resources. This paper is centered around the problem of real-time price experimentation, which is a common aspect of businesses today. In our paper, we specifically consider a firm that has an inventory of varying types of reusable resources. And from these reusable resources, the firm can group them to form different product bundles to be rented. And with each bundle, the firm can have a set of candidate price rates, which customers are charged for every period the product is used. For a given price, in our setting, we assume customers are going to exogenously decide whether to purchase on a first come, first served basis. Moreover, we assume no customers will seek to buy a product if at least one item in their desired bundle is unavailable. In other words, those customer sales are lost. Now, the firm's problem in our paper is that it does not know how customer demand and their service times will differ among the different candidate prices. And so what the firm's objective is to attempt to efficiently find which of these candidate prices is going to be best to maximize total revenue, where the total revenue is going to depend on both the demand and the duration for which customers are using these products because they are reusable. And in order to find the best candidate price efficiently, the firm is going to naturally need to navigate between deciding whether to explore a new price or exploit an existing known price in regards to knowledge of how how customers respond to these prices for different products. Therefore, to tackle this problem, we must accordingly attempt to address the question of determining both how long to test prices and how to select prices to test over time. And that brings me to discussion of the contributions of our paper, which we've organized into 3 components. The first contribution of this paper is the study of this dynamic pricing problem in the network revenue management setting to reusable resources and lost sales. And this setting is motivated by relevant applications, such as those in hospitality and leisure, where we can think about a bundle as, for instance, a car in a hotel room. There's also cloud computing, where there can exist different configurable virtual machines that can be purchased for temporary jobs. And then one last example is online retail, such as equipment rental package deals. For our second contribution, to address this problem, we propose a new learning algorithm that operates under discrete price sets that combines both price control optimization to navigate how to select prices under the existing resource constraints. And then we integrate that within this batch banded learning framework to navigate the uncertainty in customer demand and service times for different prices. For our third and last contribution, for our algorithm, we prove a new type of Bayesian regret for our setting under Poisson arrivals and exponential service times that we call heavy traffic Bayesian regret, which is a Bayesian regret in the asymptotic queuing regime where arrival rates and capacity is going to scale up proportionally. And in particular, what we show in the paper is that as the scaling parameter grows large, our algorithm achieves a heavy traffic Bayesian regret that grows as log t times n, where t is the length of the time horizon and n is the number of product bundles. To achieve our results, some challenges we must account for that we detail in our paper include blocked customers lost due to shortage of products, non-stationarity induced in the system when prices change, and the possible presence of a mixture of customers that can exist in the system at any time from different pricing schemes. In our paper, we also complement our theoretical results using simulated numerical experiments where we compare our algorithm to 2 benchmark models. Specifically, we consider 2 variations of epsilon greedy and 3 variations of a popular exploit and commit approach. And in our experiments, we further show that our dynamic approach can consistently outperform both these benchmarks. In conclusion, we consider a dynamic pricing problem in a network revenue management setting with reusable resources, and we show both theoretically and numerically that our proposed learning algorithm can very efficiently learn best price to maximize total revenue. Thank you for your time.